Pont Casalte Aqueduct is an industrial wonder which has just been nominated for World Heritage status. It's a major achievement by one of the greatest engineers of the Industrial Revolution, Thomas Telford. It was Telford who in 1826 built the Menai Bridge, one of the first modern suspension bridges in the world. Pont Casalte used new technology to defy gravity. But how was it built? Built in 1805, Pont Casalte is the longest and highest aqueduct in the United Kingdom. As part of the application for World Heritage status, the Royal Commission has undertaken a new survey. For the first time, the story of how the aqueduct was constructed is being uncovered with the help of modern detective work and digital technology. Telford began his career on a high.
At the middle of the aqueduct here, you really do see the height, don't you? Above the height of these enormous oak trees. It's a spectacular view.
And when you're looking down, I mean, we're over 40 metres high here above the sort of level of the river, and it's
120 feet in my money.
It's absolutely stunning, isn't it? What a feat of engineering. It's amazing.
And the imagination of it. Nothing like this had ever been built in the world.
The aqueduct was bold in design and construction, and aspects of the build have puzzled generations of engineers and surveyors. For the first time, the recent survey uncovered how Telford and fellow engineer William Jessup erected this skyborne canal over a 10-year period. One of their principal challenges was to reduce the weight to make the structure viable. The solution they came up with was cast iron.
From up here, you don't get a real impression of just how thin the plates are that make up this. I mean, they're only about 3/4 of an inch thick, aren't they, the actual iron plates?
It's like a really huge Meccano set being put together when they were here constructing it.
This is where you can actually see just how thin those cast iron sections are. I think a lot of people going over here feel fairly secure because they look at the depth of that and they think that's the depth of the ironwork. But where the little flange is broken there you can see it's only 3/4 of an inch thick, holding all this water in. You could never do that in stone, could you?
You certainly couldn't.
To maintain flexibility, the trough isn't bolted to the supporting structure, but is held in place by the weight of the water.
And this, of course, is the plug hole.
Okay.
If you lift that lever, all the water runs out of the aqueduct. I've always wanted to do that, but I think it's got a bolt in it to stop me.
To supply materials for the project, Telford and Jessup required a huge construction yard. The Royal Commission have worked out that it was almost certainly sited in what is today the busy basin of the canal. We can only imagine what it looked like.
Those are the unsung heroes, really, all the people who actually built the canals, and we've got no evidence, really, about where they lived. You look over here and there's the Telford Inn, as it's now called, which was where the resident engineer lived and could oversee the works, and he could watch every block of stone being cut.
I mean, it must have taken a huge amount of people. It's hard to imagine how many would have been involved.
Yeah. Millions of tonnes of soil being moved, and skilled work and navvy work.
So you can imagine this area now. Obviously there wouldn't have been the basin here, any water. It would just have been a levelled area with sort of, temporary structures, huts, and just large areas for laying out all the ironwork and the stone. Yeah,
until you really start to think about it, you don't imagine what the problems were, do you? The sheer amount of space they must have needed to prepare the work for that structure.
Behind the scenes, there was tension and competition between senior partner William Jessup, regarded as the finest engineer of his day, and the young Telford. Modest and retiring, Jessup was pushed aside by Telford, who claimed the credit for himself. Big egos tend to rise to big challenges, including how to create a level structure at such a height.
The embankment here really is an amazing structure, isn't it?
Oh, fantastic. I mean, the sheer scale of it is probably one of the largest sort of earth-moving episodes of the sort of 18th century, really, when it was being constructed. And it stands sort of 28 metres high. It's lost a bit today because of all the trees, but they were planted partly for the stability of the actual earthwork.
Telford recommended planting trees on his embankments and cuttings to make sure that they stayed put. And all of that, dug with shovels, moved on boats and rails. Amazing project. It's just a tiny person on the top.
Yeah, just to give an idea of the sheer scale of it.
One of the key mysteries, how the piers and arches were put up, has been resolved by the new survey.
This is the easiest span to get a good look at up close, isn't it?
Yeah, definitely. We're at the right height.
And your computer model that you've been developing is based on this arch, but all the arches are the same.
Everything's the same, you've got all the spans are the same, and you're looking at a structure, but often it's quite hard to understand how it was built when you're just seeing it in situ built, and we've been trying to understand the actual sequence and method of construction. The curving ribs here, which were actually in 3 separate sections, you can see the joins above where they were bolted into place.
So one curving up, one across the top, one down.
But imagining the fact of the trough above really just sat on top of all these ribs. It wasn't really bolted into place, but in essence the weight of the water was holding everything into place.
Although the aqueduct is a miracle of modern technology, Welsh flannel was used to waterproof the trough.
Must be the only aqueduct in the world to waterproof with Welsh flannel. It's amazing, isn't it, that there are no drips. All those tons of water going over and no drips.
The new survey reveals that the piers were raised in stages between 6 and 8 metres high, moving south to north across the Dee Valley. The clues are in the stonework.
I think what stands out most obviously is the 2 larger stones here that are jutting out from the face. Now this is a real key to how the actual stone piers were constructed. You've got in your hand perhaps something that helped us, guided us towards wondering how the stone was constructed. This was a contemporary drawing, and it shows these strange sort of gangways running across the structure. At first we didn't think until we actually came and really started looking, you notice irregularities into the stonework. Now if we turn and look across to the pier behind us, you'll see amidst the rectangular stonework 2 small square stones. Now that's the key, that is at exactly the same level as the large stones behind us here. And originally they would have been slots which held large timber posts running all the way along the whole length of the aqueduct, upon which platforms were constructed for conveying the material from the construction yard on the Trevor Basin side. That's the key really, because the key really was how do you get all the building materials which are amassed at one site on the north side of the river all the way across to the south side.
And then presumably when you've got here, you'd use something like this crane to lift the stone up.
In place.
And we can see some
there's a few
manoeuvring a block into place.
The giddying height of the 18 piers posed problems for engineers and workers, creating a demand for lightweight technology. Telford and Jessop's solutions were brilliant. The columns were tapered to the minimum possible dimensions, giving an effect of slenderness. The pillars were also hollow at the top, which reduced the weight and made working safer.
We can also see what Jessop said about the upper parts being hollow, which was a unique innovation at the time, wasn't it? And Jessop said he proposed the upper sections be hollow. It will save £500 or £600 in expense, and what to me appears most material, it will afford safety to the workmen, because they could work from the inside out instead of the outside in.
I think in many ways the platforms also were a lot nicer way to work on. You'd imagine all the scaffolding, having to climb up all the scaffolding from the bottom up, because that really would give you the sense of, you know, be quite frightening really.
They really are ideas, aren't they? I mean, it's enormous.
I think it was reported that only 1 person actually died in the construction of the aqueduct.
According to Telford, who also said, and that through his own fault.
Yeah, exactly.
More than 200 years after Pont Cysylltu was built, it's only now that Telford's innovative thinking is being revealed.